Bismillah Rahman Rahim. Welcome to the very interesting topic, which is the nuclear energetics. So let's move to the learning objective. I am going to explain mainly 4 learning objectives in this lecture. So the first one is the calculation of Q value using mass difference of reactant and products, and calculation of Q value using energy, and basically it is the kinetic energy difference of the product minus reactant and its derivation. And the third one will be the derivation to calculate the energy of the product nucleus. And the fourth one, we will be discussing about some exercises on the calculation of Q values and energy of the product particle. So these are the main learning objective, and basically which are covered under the heading of the nuclear energetics. So let's move to the first one objective. This one is the very simple representation of the nuclear reaction. That means the bombardment of the projectile on the target, and it will form the composite nucleus, or we call it the compound nucleus, and then which is disintegrated into the product nucleus and the product particle, and collectively it is called the products. So let's have the example of this nuclear transmutation is the bombardment of the alpha and the production of the proton particles. And this is the simple representation of the nuclear reaction. Any of the target, when it is bombarded with the alpha particle, it forms the compound nucleus with the increase in 2 atomic number and increase in 4 mass number. When the one of the product particle is proton, that means that the other product nucleus or the daughter nuclide is having 1 atomic number more as compared to the parent, and 3 mass number is increased in daughter as compared to the parent. So simply you can sum of the products part. This will be the Z plus 1 plus 1 Z plus 2, and in this compound nucleus is Z plus 2. Again, this is plus 3 1 plus 1, this will be plus 4, and similarly you can add up the reactant part Z plus 2 and A plus 4. Similarly, you can go from the reactant side or from the product side towards the compound nucleus. So it is just the sum of the atomic number and the mass number. So this is the simple representation or the short form of the nuclear reaction. It is shown by the heavier nuclide outside the bracket and lighter one within the bracket. So in the lighter one, the first one is the projectile, and the second one is the product particle. So these are the lighter ones. So this is the real example, like in case of the nitrogen 714. So this is the stable nuclide. When it is bombarded with the alpha particle, it forms the fluorine 918, and this disintegrated into the proton and the oxygen with the atomic number 8 and 17. And similarly, you can just the sum of the atomic number and the mass number on the both sides to balance the nuclear reaction. So this is the short representation of this nuclear reaction, and similarly there are a lot of the other examples you can do. So we were just here we want to calculate the Q value, which is the energy released or the absorbed in a nuclear reaction. And this is the simple nuclear reaction: capital X, small s, capital Y, small y, and capital X. In throughout this video, I will be using as the target. Small x will be the projectile, Cn will be the compound nucleus, which is the intermediate, Y is the product nucleus, and small y will be the product particle, and this will be the energy release or absorbed, and it may have the minus sign or the plus sign depending on the nature of the nuclear reaction. So this is the simple equation. That means we are just taking the difference of the masses of the reactant side minus masses of the product side, and this is the difference in the masses multiplied by the c square. This is actually the Einstein equation, E is equal to mc square. And if you have just to put the values and you just have the difference in the masses will be minus 0.001282. So multiply this factor 931.5, it will directly convert the mass into the energy. And this is the actually the conversion factor. 1U will be equal to 931.5 mega electron volt. So energy is minus 1.19. So energy is absorbed. Here the minus sign is indicating that the energy is absorbed, and this reaction is called the end-Orgy reaction. So this is the simple way to calculate the Q value by using the differences in masses. So this was our first objective. So these are my other two videos. If you want to go to in detail of the other nuclear reactions, or there are a lot of other transmutations by alpha, by proton, or deuterium, or the neutron, or the gamma, you should visit my other YouTube videos where you can find the further detail. So moving to the second and third objective, that means it is the calculation of Q value by using the difference in energy. So this is the advanced concept as compared to the previous one. So there are two ways you can calculate the Q value by using the difference in mass, and you can uh, calculate the Q value by using the difference in the energies. So again, this is the same nuclear reaction I am showing here: target, projectile, product nucleus, and the product particle. So I know I'm going to derive the equation with some logics. So what is happening in this derivation? So this is, as a chemist, you must understand all the steps which are going to be used to derive the equation. So this is the actually the main learning in this video. So what I am going to do, I am going to assume the target is at rest, and hence it has no kinetic energy when bombarded with the incident particle X with the kinetic energy Ex. So I am assuming here the target is at the rest position. So when it is at the rest position, it does not has the kinetic energy, but it has the mass. And of course, projectile must have the mass and the energy as well. And product nucleus and the product particle also have the mass and the energy. So the only thing is this target is not having the kinetic energy because of it is present at the rest position, or you can say because the target is the stable nuclide. So we want to make it a non-stable or the radioactive nuclide, or this is one of the way for the artificial disintegration. So this is all about the what I have explained above by using the law of conservation of energy. So considering the mass and energy balance, we can write this equation. So I have written over here, this is the target. So this is the mass of the target, and it does not has the kinetic energy. And now the projectile, this is the kinetic energy of the projectile, mass of the projectile, kinetic energy of the product nucleus, mass of the product nucleus, kinetic energy of the product particle, and mass of the product particle. So actually these are the as small m and x represent the projectile. Capital M and capital X is the target as shown over here. So small m y is the product particle, and capital My is the product nucleus. So these mc square, mc square, mc square with the xx, yy are actually the rest energy, and estimated according to the Einstein relationship is equal to mc square. So this equation I am going to use to further go through the equation. So this is the, as we have explained in the previous slide. Now I am just rearranging the equation. So I am removing the bracket sign. So this equation will become like this. And after this one, now you just arrange the mass uh, to the one side or energies to an other side. So moving to the mass of M capital Y or M small y, these are the product nucleus and the product particle to the left hand side. So the sign will be the minus. So if you move the energy of the projectile to the right hand side, so this will become the minus. So actually this will be the, after taking the c square as a common, this equation becomes like this. And this is the actually the Q. So now this you can understand, the Q may be the difference of the masses as represented over here in equation number 1, or Q may also be the difference in energy as shown with the equation number 2. So therefore the Q value stands for the energy balance, commonly known as the Q value, so for of a nuclear reaction. Now, this is looks like easy, but it is not the easy case to actually to calculate the energy of the product nucleus. So this was our third objective. Now I'm going to solve this one further. Actually, the now the purpose or the major objective from onward is the to find out the energy of the product nucleus, which is heavier, and then I'm going to just put the value of Ey over this equation to get the final equation. So here again, capital X is the, this is the target having the mass of mx, like it is again shown over here. It is being bombarded with the uh, projectile with the mass mx moving toward the target with the velocity of vx. So that means this target is bombarded with the projectile having mass and velocity is this, and this is called the momentum of the incident projectile. So when the target is hit by the projectile, so there is the two products are formed, like capital Y or the small y. So capital Y is the product nucleus having the mass of capital M and capital Y moving towards this direction with the velocity of Vy. So this is the momentum of the product nucleus. Mass into velocity is the momentum. Similarly, the product particle is formed moving to the this direction with the like circle here small y with the mass of my, and it is moving toward this direction with the velocity of vy, and so mass my, velocity vy is the momentum of the product particle. So we are assuming here the product particle form a right angle with the incident particle or the projectile. So right angle means the angle between small m and small y is the 90 degree. Even you can take a angle from here or the here. So this is all about this representation of this nuclear reaction by using this diagram. Now I'm just connecting this y point to the this point, let's suppose this is O, and then connecting this O with the this small y. So this is the uh, actually, if you keenly look on this one, this is one right angle triangle. Why it is the right angle? Because the angle between is the 90 degree. So this is also another right angle triangle, and because the angle between this is also 90 degree. So both are the triangle are similar to each other. So if you have a look on this one, as we have already explained, this is the momentum of the product particle. So this line will be similar to this line. So this will also be the momentum of the product particle. Similarly, this line is similar to this line. So xy will be equal to the oy, and this is the momentum of the product nucleus, and this will also be a momentum of the product nucleus. So this is all about the representation of this nuclear reaction on a diagram. Now I'm going to solve this any one triangle. You can take this one or you can take this one because both are similar to each other. So I am using XYO triangle. So it is the right angle triangle. I am using this Pythagoras theorem. According to this one, this xy square will be equal to oy and ox. So this xy will be equal to the sum of the oy and the ox. So you take this square on the both side. So therefore, put the value of the xy. Xy is the capital M, capital Y, capital V, capital Y. So I'm just putting the value of xy. So oy is this. So this is the value of oy, small m, small y, small v, small y square, and then xo is this, and this is the mass into velocity of the projectile. So I'm just putting the value over here. These are the square, and now in the third step, I'm just multiplying the half with the whole equation. So multiply both the three terms over here, and then now the relationship between the kinetic energy and the masses can be developed by just rewriting the equation as in this form. So here I am just splitting the m square into the m, that means in the both forms. So similarly, just splitting this m square and splitting this mx square. So again, just rearranging the equation, just putting v square over here. So this equation will become like this one. So if you have a look on this equation, this half mv square is the kinetic energy. So I'm just putting the kinetic energy in place of the half mv square. So here is this is the E capital Y. E capital Y is the energy of the product nucleus. M small y and V small y, it is the kinetic energy of the product particle. And similarly, M small x and V small x is the kinetic energy of the projectile. So I'm replacing the half mv square with the kinetic energy. So this equation becomes like this. Now this is very easy to calculate the energy of the product nucleus. This was our objective. So just dividing the capital M, capital Y with this equation. So you can get the value of the capital E, capital Y, or this is the energy of the product nucleus, which was our one of the objective. So you can calculate the energy of the product nucleus by using this one, but our target, the the third one target was to calculate the Q value, and in this equation, this was the equation we have already discussed before. So I'm just putting the value of Ey over here. So by putting the value of Ey, this equation will become like this one. So this is the equation, and further I'm going to just the rearranging the equation. So I'm just splitting the both value, dividing with capital M, capital Y with each of the values over here. So this equation becomes like this: Ey my over my, ex mx over my, and these will remain the similar. So again, rearranging because I want to take a common. So I'm just putting e small y over here. So the equation becomes like this. And now I'm just taking the common ey from this part. So this part will become like this. And here I am just taking the minus ex as a common. So the rest will be the bracket like this one minus mx divided by my. So there is no difference between these two equations, just to rearrange and to use in a simple form, you can use this equation. So actually this is all about the final equation to calculate the Q value. So what we have done over here, we just put the value of the product nucleus, product energy of the product nucleus in the equation, and we are getting the final equation to calculate the Q value is this. This is the extension of this equation. This is because there are now the three terms, first and second term. We have already discussed. This is the third term, but this becomes insignificant due to the two reasons. The first one is due to this capital M, capital Y. This is the mass of the product product nucleus. So when the mass of the product nucleus increases, that means this whole values become less significant because the value will be negligible. And the second reason is we have assumed over here the angle between the incident particle and the product particle is 90 degree. And when it is 90 degree, cos 90 will be equal to 0. And when it is 0, the whole third term becomes the 0. So again, this will move to this equation. So actually, this is the equation we will be using to calculate the energy of the nuclear reaction with the difference in the kinetic energy. So the fourth and last objective, now I'm going to show the different calculation to calculate the Q value by using this equation. And the question is, when boron is bombarded with 1.510 megaelectron or deuterons, the following reaction occurs. So this is the boron bombarded with the deuteron forming alpha particle and the beryllium. And the alpha particle coming off at the angle of 90 degree with the direction of the deuterium beam have an energy of 6.370 mega electron volt. And what is the value of the Q? So the energies are given. So no, you have to use this equation because energies are given, and you have to use this equation instead of the difference in the uh, masses which we have used in the first slide. So simple, because the angle between the incident particle and the product particle is 90 degrees. So again, 90, you put the 90, this will become the 0. So this will be the final equation. So data is here. Ex is the energy of the projectile, which is 1.510 in case of the deuteron. Energy of the product particle, which is alpha, and this is the 6.370. And these are the masses, and you can get from any table available in the literature. The mass of the deuteron is the small mx, it is this, and the mass of the alpha is 4.003877 AMU, and the mass of the product particle, which is beryllium in this case, it is 9.0 so on AMU. So just you have to put the values in this equation. So I'm just putting the value over here. You can get the value of Q. Just rearranging the equation, you can LCM, you can directly calculate. So I'm just showing more steps so you can easily understand how to calculate the Q value. So I have just taken the LCM over here. Then you can solve these two uh, terms, and the values will be this, and the final Q value will be 8.026 mega electron volt. So this is the way to calculate the Q value by using the difference in the energies and the masses. So other one is how can you calculate the energy of the product particle. So the question is, when boron is bombarded, this is the same nuclear reaction we have solved before, boron with the deuterium, but here this deuterium is bombarded with the same energy, but it will form the product particle of proton instead of the alpha. So when proton is formed, again this will be the boron, because there is no difference in the atomic number on the both side, reactant side and the product side. So it was found to occur and to have a Q value of 1.136 mega electron volts. So what is the energy of the proton or the product particle observed at 90 degree? Again, it is 90 degrees, so 90 cos 90 will be 0. So this equation becomes this. So again, data is given, Q is 1.136. The energy of the projectile, in this case is the deuteron, and it is 1.510. Energy of the product particle you have to calculate, which will be in mega electron volt. Mass of the deuteron is small, is this, mass of the proton is this, mass of the boron is this. So again, you should use this equation. So only this is missing, and this you have to calculate by using this data. So I'm just again, when you put the value, just multiply and plus, and after this one, you have to divide this by 1.083885, you will get the value of 2.2079 mega electron volt. So this is the energy of the product particle, and in this case, it is the energy of the proton emitted with the bombardment of deuteron on the boron. So this is all about the four objective and nuclear energetics we have discussed in this lecture. So again, these are the references if you want to further study. These are our own books. Actually, these are the books of my supervisor, Professor Dr. Iftikhar Imam Naqvi, who is my mentor, my supervisor, research supervisor, who wrote these two books and published. And there is another third one book, Nuclear Physics by Kaplan. And thanks for watching. These are my other playlist. You can find, I am just rearranging all the videos relevant to the nuclear chemistry in one channel. You can go through the channel and watch the other videos, or you can subscribe to my channel. You can just search by using my name, or you can follow the link, and you can watch the other videos relevant to the nuclear chemistry or the other branches of the chemistry. Thanks for watching, and see you in the next lecture.